So good evening everyone. This is Nirosha. In this session, let us see about a physical chemistry topic, that is solutions. So let us see all the concepts in the solutions, and let us see few questions also regarding this chapter. Okay, now let us see the basic definition. What is meant by a solution? So what is a solution? It is a mixture of two or more components, that is, it is shown in the slide. It is a mixture of two or more components, which is a homogeneous mixture or a heterogeneous mixture. Let us see in detail. See, a solution is a mixture of two or more components. For example, if we take salt in water, it means we are taking salt in one beaker and water in another beaker. If we are mixing both of them, it is a solution. So in that, one is the solute and another is the solvent. So let us see what is a solute. Here the component which is in lesser amount, which is in small amount, that is known as solute, and the component which is in large amount, it means more significant amount, means which is in large amount and determines the physical state, either it is a solid or a liquid or a gas, that can be determined by this solvent, that is known as the solvent. Remember, solute is a which is a lesser amount, that is known as a solute in a solution, and which is in more in amount, that is known as solvent. And both the mixture of this solute plus solvent is equal to solution. So remember, this is the basic concept, and let us see how these solutions are classified. These solutions are broadly classified into two ways. One is homogeneous solution. See, homogeneous solutions. For example, if we are taking a mixture of salt and water, what happens after some time? If we add salt to the water, the salt is completely dissolved in that water. That type of solutions are known as homogeneous solutions. It means solutions with same composition and properties throughout the solution. These are known as homogeneous solutions. We have examples here. Solutions of NaCl, just now we have discussed. Similarly, sugar in water. And next, cough syrup, a cup of coffee. It is mixture of milk and the coffee powder, right? Yeah. And mouthwash and perfume. These are few examples of homogeneous solutions. And next, heterogeneous solution. What is meant by heterogeneous solution? Opposite to this homogeneous solution, which are not soluble throughout the solutions. See the definition? Solutions with not the same composition and properties throughout the solution. These are known as heterogeneous solutions. For example, it is a mixture of oil and water. If we mix oil and water, they won't mix, right? They form a separating layer. That type of solutions are known as heterogeneous solutions. Water and sand mixture. Water and sand mixture, they cannot be soluble. And water and chalk powder, there will be a precipitate in this mixture. So this type of solutions are known as heterogeneous solutions. We have different types of solutions, different types of solutes mixed in different types of solvents. For example, if we mix solid, they are examples of alloys. They are mixture of different minerals, right? And solid and liquid, if we mix solid with liquid like sugar and water solutions. Next, solid and gas like iodine vapors in air. In air we have number of gases. In this we will mix a solid, we will take a solid iodine that is easily evaporated and mixes with the air, that is iodine vapors. That is a type of solid and gas solution. And next, liquid in solid. For example, mercury in metal amalgams. Most of the metals react with mercury and forms their respective amalgams. That is a type of liquid solid solution. Liquid in liquid like alcohol in water, and liquid in gas, liquid with gas like moist air. Moist air means it consists of water in it that mixes with this air, remaining gases, that is moist air. Next, gas in solid like occluded hydrogen on palladium, platinum and nickel. This you can see in electrolysis. And gas in liquid like aerated water, you can see in soft drinks. And next, gas in gas, that is air. These are the few examples of solutions. And here you can see what is a saturated and what is an unsaturated solution. What is a saturated? Here you can see the definition: a solution which contains as much solute as it can dissolve at a given temperature. So how much amount of solute can be dissolved in the solvent at the particular temperature, that is shown by this saturation. If excess of solute is added, that cannot be dissolved. That type of situation in a solution is known as unsaturated solution. It means a solution which contains lesser solute than the amount of solute it can dissolve. See, for example, if we take, suppose a 1 gram of sugar completely dissolves in 10 ml of water. Suppose if we take in this way, if we take this is a complete saturated solution. It means the 1 gram of sugar is completely dissolved in that water. If we take excess amount of this solute, that is excess amount of sugar, that cannot be dissolved in that solution, that type of solution is known as unsaturated solution. This is the difference between them. And next, this strength of the solutions, how much percent the solute can be dissolved in the solvent, and how the solution strength is determined by few terms. Let us see those terms here. First, it is mass percentage. Mass percentage, in the name itself, it is completely depending on the mass. So you can see the definition. It represents the mass of the component in 100 grams of solution. See, if we take a solution, if the mass of the solute is 100 grams, how much percentage this can be dissolved in that solution is determined by this mass percentage. See, this percentage of the component, mass percent of the component, is equal to mass of the component in the solution into 100. Since it is percentage, we are multiplying it with 100 by its mass. And next, for example, the mass percentage of the glucose in 100 grams of solution containing 10 grams of glucose. For example, if we take such type of solutions, what happens? Mass percentage of the glucose is equal to mass of the glucose in the solution into 100. This is the main term. We need to take mass of the glucose, that is multiplied by 100. That gives the mass percentage of glucose. And next, volume percentage. Similarly, to the mass percentage, we can also calculate the volume percentage. So it represents the volume of the component in a solution of 100 ml. The main term here is the volume of the component in 100 ml of solution. Here we need to calculate the percentage of the solute, how it is dissolved in the solution. See here, it is given by the formula volume of the component into 100 divided by total volume of the solution. This shows the volume percentage. And next, weight by mass by volume percentage, that is shown by this. Here we need to mix both this mass and volume. It represents the mass of the solute in gram dissolved in volume, that is 100 ml of solution. That is, the mass percent by volume is equal to mass of the solute which we take in grams divided by volume of the solution which we take in ml into 100. This gives mass by volume, that is W by V percentage. And next we have one more term, that is concentration in parts per million. It means in a millionth part how much amount of the solute is dissolved. You can see when any amount of the solute is present in million, that is 10 power 6 parts of a solution. How much amount of solute is mixed with 10 power 6 the millionth part of a solution, that is known as parts per million. That is given by the formula mass of A by total mass of the solution into 10 to the power of 6. Here this 10 to the power of 6 represents the millionth part. Similarly, we can also see concentration in parts per billion. It means how much amount of the solute is present in 10 to the power of 9th, it means billion part of the solution, then it is known as parts per billion. See, it is given by the formula ppb, that is parts per billion, that is equal to mass of A by total mass of the solution into 10 to the power of 9. So this is parts per billion. And next, molarity. This is the main concentration term. What is meant by molarity? It is denoted by M. So it is the number of moles of solute present in 1 liter volume of solution. Number of moles of solute divided by volume of solution. See, you can see here how we can calculate number of moles of solute. This number of moles of solute is calculated by weight divided by gram molecular weight of any compound. So that is shown here, this molarity. Molarity is equal to weight of the solute in gram by molar mass, that is gram molecular weight. This shows the number of moles. This is the ratio of the number of moles, that is divided by volume of the solution, that is we are taking it in liter. So this is the formula for molarity of the solution. Remember this, it is very useful in solving problematic questions. If suppose in case of dilution or mixing 2 or more solutions, if we need to calculate molarity or volume, then what we will do is we will equate it in this way, that is M1V1, that is molarity and volume of one solution, is equal to molarity and product of molarity and volume of the other solution. And if third solution is also mixed, it is M3 is into V3. It is molarity into volume of the third solution. In this way we can calculate the mixture or diluting solutions. You can see here, if we need 1 of the molarity, then if there are 2 solutions and if we need 1 of the molarity, then what we do? We will add the sum of the M1 V1 plus M2 V2 by, will take average of the volumes, that is V1 plus V2. So this is also one of the important formula. If 2 solutions are added and if we need 1 of the solutions molarity, will divide, we will add those M1 V1 plus M2 V2 and divide the volumes of the addition of the volumes. In this way we will get the molarity of the solutions. And next, one of the important term, that is molality. See the difference between molarity and molality. This is denoted by small m. Molality is denoted by small m. So let us see what is molality. It is number of moles of solute, solute dissolved in 1 kg of solvent. In molarity we are taking volume. In molality we are taking 1 kg of solvent. Here also we are taking weight of the solvent. This is denoted by small m. Here this molality is given by the formula weight of the solute in grams by molar mass, that is number of moles, into weight of the solvent in kgs. So this is the formula of molality. See, if molality is 1, if this value is 1, then that is known as 1 molar solution. And if concentration of 1 molar solution is less than that of 1 molar solution, see, concentration of 1 molar solution, that means this type of solution, is less than that of 1 molar solution. See, molar solution concentration is less compared to that of molar solution. This molality is preferably over molarity. Molality is used mainly in the experimental calculations, and thus molality is independent of temperature while molarity is dependent on temperature. When there is volume term in any formula, it is dependent on temperature. That's why molarity is depending on this temperature, while this molality we don't have any volume term, so this is molality is independent of this temperature. And next, normality. This is also one of the important term. So what is normality? It is the number of gram equivalents. Here you have a new term, gram equivalents of a solute present in a liter of a solution, similar to the molarity, but there we are taking gram molecular weight in the denominator. Here we are taking gram equivalents or equivalent mass. Here the gram equivalents present in 1 liter volume of solution, it is denoted by capital M. So this N is equal to weight of the solute in grams by gram equivalent mass into volume in liter. So this is the definition of normality. So let us see a relation between this normality and this molarity. Here normality is depending on equivalent mass. That normality into equivalent mass is equal to molarity into molar mass. This is equal to weight of solute by volume. So both these multiplications is equal to weight of the solute by volume. So this is neglected, and if we take a relation between these two terms, this normality is equal to molarity into the valency. The valency here, the ratio of this molar mass and this equivalent weight, which gives the valency. Valency is equal to here molar mass divided by equivalent weight. So this gives the relation between normality and molarity. Normality is equal to molarity into valency. Or we can also write in terms of H plus and OH minus ions, that is normality is equal to molarity into number of H plus or OH minus ions present in the compound. So this is the definition regarding normality. And next, let us see mole fraction. What is meant by mole fraction? In the term itself, it is having a fraction. So it means a fraction part is determined by this term. Here, this mole fraction of a component is given by the moles of the one component divided by the total number of moles present in the solution. It is denoted by X, capital X. This mole fraction is denoted by capital X. Here, what is this mole fraction? It is the number of moles of the one component, that is either solute or a solvent. It is having the ratio of this number of moles of the solute or a solvent to the total number of moles present in that solution. If we are taking for X A, either A may be solute or a solvent, this mole fraction is given by number of moles of A to the total number of moles present in the solution, that is A plus B. If we take it for B, it is NB by Na plus NB. See, here we are taking A as a solute. So Na becomes number of moles of solute and NB becomes number of moles of solvent. And here the weight percentage, as we have seen earlier, the weight percentage formula, volume percentage formula, it is shown here. So these are the few terms which are used to determine the strength of any solution. And next, let us see what is meant by solubility. This solubility is mainly given by the how much extent of a solute is dissolved in the solvent. You can see the solubility of a substance is its maximum amount that can be dissolved in a specific amount of solvent, that is known as solubility. This solubility mainly depends on the nature of solute and solvent. Nature of this solute and solvent, how much easily a solute can be dissolved in a solvent, and the interaction between them, the bonding, how the new bonds can be formed between the solute and the solvent. This is the dependent factor. So the strong attraction between solute and solvent molecules, this will give the maximum stability. And next, the molecular size of the solute. Since to form a solution, a solute molecule must be forming a new bond or mixes with the solvent molecule. So the size of the molecule is also the dependent factor. You can see larger molecules are more difficult to dissolve in the solvents. If the molecule size of the solute is large than the solvent, it is difficult to dissolve, whereas smaller molecules dissolve more quickly in the solvent. And next, polarity. See, this is also important factor. What is polarity? So let us see. There are two types of solvents, majorly polar solvents and non-polar solvents. Polar solvents, for example, what are polar solvents? They are having bonds with different electronegativities, mainly like water. Take example as water, ethanol and formaldehyde. They dissolve polar solutes which can form bonding easily, which have more electronegative nature. They are known as polar solvents and they can dissolve any type of polar solvents, polar solute type bond forming type of solutes, whereas non-polar solvents, these are opposite to this polar solvents like benzene, pyridine, toluene, hexane. These can dissolve only non-polar solutes. It means like dissolve, like polar solutes are dissolved in polar solvents, and similarly non-polar solutes are dissolved in non-polar solvents. And one more factor, that is temperature. If we increase the temperature, what happens to the solubility? Increases. And pressure, this pressure also increases this solubility. How this pressure affects this solubility, it is shown by Henry, that is the Henry's law. This is also one of the important law in this chapter. So what is this law? So this law states that solubility of a gas, that is how much extent a solute is dissolved in the solvent, it is in a given volume of a liquid, in a particular volume of a liquid at constant temperature, is directly proportional to the pressure of the gas. See, the amount that is simply known as the M, that is directly proportional to P. Here we are taking gas as a solute. Here it is dissolved in a liquid with applying pressure at constant temperature. This M is the mass of the gas and P is the pressure applied. This is directly proportional, this mass of the gas which we are taking is directly proportional to the pressure, that is given by M is equal to K into P. Here K is known as Henry's constant, or it can be given by M by P is equal to KH, where P is the pressure and M is the mass of the gas and KH is Henry's constant. Here when solubility is expressed as its mole, if we take in terms of mole, this mass is taken in terms of mole fraction. See, that is shown here. P is directly proportional to X, that is equated by the Henry's constant. This is the relation. So now let us see, this is the graph. If we take graph between pressure and mole fraction, there is a linear straight line from the origin. So this type of line is shown if we take a graph between mole fraction and pressure, and where we will apply this Henry's law. This can be applied in soft drink bottles which are sealed at high pressures to increase the solubility of carbon dioxide gas. As we can see in soft drinks, there is a pressured carbon dioxide gas in it, that is the principle involved in it is Henry's law. And the sea divers uses a mixture of oxygen and helium to minimize the painful effect of nitrogen. So this is one of the use of this Henry's law. And at higher altitudes, at higher places, the breathing becomes tough as oxygen is less available. In these places also, due to the less pressure, the oxygen cannot be supplied that much freely. By applying this Henry's law, this oxygen supply in that higher altitude places can be easier. And next we have one more important law, that is Raoult's law. This is one of the important law in this chapter, where most of the questions will come from this law. So let us see what is meant by Raoult's law. It states that for any given solution, the vapor pressure of a component for a given temperature, see here the temperature is given and we are considering vapor pressure of the component, how much pressure, vapor pressure is applied on that component, that is equal to the multiplication of mole fraction of the component. We are taking mole fraction of this component in the solution and vapor pressure of the component in its pure state for the same temperature. Before, here we are taking two types of vapor pressures. Vapor pressure of the component of a solution. After adding a solute, we are taking vapor pressure of the component. We are determining the vapor pressure of that solution, that is equal to the multiplication of mole fraction of the solute, mole fraction of the solute in the component, and vapor pressure of the component in its pure state. Before adding a solute to it, the vapor pressure in it is considered. See, that is, in its pure state, the vapor pressure is given by P0 A. For the solution, it is PA, and XA is the mole fraction of the solute. If we take for PB, it means for B, it is, if we assume it is a mixture of A plus B. If we take for B, it will be P0 B into mole fraction of B. So this vapor pressure for a solution containing two components A and B, the total vapor pressure P, is the PA plus PB, vapor pressure of PA plus vapor pressure of PB. So that is given by the Raoult's law, P0 A of XA plus P0 B of XB. So this total vapor pressure can be given by using this Raoult's law with the help of this formula. Remember this. And next, this is for volatile solutes. It means what is volatile? Which can be evaporated easily. This is applicable for volatile solutes. When it is, if we take for non-volatile solutes, what happens? For non-volatile solutes, the Raoult's law states that the relative lowering vapor pressure of the solution containing a non-volatile solute is equal to the mole fraction of the solute in the solution. Here, what is the main term? Relative lowering of vapor pressure. That is given by this P0 minus PS by P0. What is P0 here? P0 is vapor pressure in of pure solvent. This is vapor pressure of pure solvent. What is PS? PS is vapor pressure of the solution. So this, the difference between vapor pressure of the pure solvent minus vapor pressure of the solution to the ratio of P0, that is vapor pressure of the pure solvent, that is known as relative lowering of vapor pressure. If that is equal to mole fraction of the solute in the solution, then that is known as the Raoult's law for non-volatile solutes. So for non-volatile solutes, this is the formula to be applied, and this is the most important formula. Here X2 is the mole fraction of the solute, and where this mole fraction of the solute can be determined by the formula of the mole fraction, N2 by N1 plus N2. N1 is the number of moles of solute, and N1 is number of moles of solvent, and here, and N2 is the number of moles of solute. Here, as we have discussed, PS is the vapor pressure of the solution, and P0 in its pure state vapor pressure. So this is about Raoult's law. So from this Raoult's law, we can define ideal solutions and non-ideal solutions. What are ideal solutions? So an ideal solution is the one in which each component follows Raoult's law over the entire range of temperature and concentration circumstances. If we change temperature or concentration in the given solution, still it follows the conditions of the Raoult's law, then that type of solutions are known as ideal solutions. And next, opposite to this is non-ideal solutions. It means they will be deviated from Raoult's law. See, when a solution deviates from Raoult's law over a broad concentration. If there is a change in the concentration, then we can observe the change in its behavior from deviation from the Raoult's law. That type of solutions are known as non-ideal solutions. These solutions do not follow Raoult's law at every concentration range and all temperatures. If temperature difference is also there, then they will be deviated from the Raoult's law. Such type of solutions are known as non-ideal solutions. Simply remember, which obeys Raoult's law, they are ideal solutions. Which do not obey Raoult's law, they are non-ideal solutions. You can see here the Raoult's law. Here you can see a graph which is between vapor pressure and mole fraction. Vapor pressure and mole fraction. For ideal solutions which obeys Raoult's law, they have a linear lines without any deviation. They have a linear lines. You can see here this total vapor pressure, this PA, this total vapor pressure is sum of this PA plus PB. There is no deviation in all the lines. So this is seen in ideal solutions. When coming to non-ideal solutions, non-ideal solutions, you can see two types of deviations here. This is above the ideal behavior. This total pressure of the solution is above the ideal behavior. It means it is showing positive deviation from Raoult's law. You can see here every line is above its original axis, that is, it is showing a positive deviation. Here it means you can see here the vapor pressure of PA is equal to mole fraction of its XA and P naught of A. It means in its pure solvent the vapor pressure of its the solute in its pure state. Here also PB is equal to XP into P naught B. The total vapor pressure is sum of this PA plus PB. But what happens in the positive deviation? The PA value is, total vapor pressure value is, total vapor pressure of PA is greater than its product of its mole fraction and its vapor pressure in its pure state. You can observe PA is greater and PB is also greater. It means sum of this PA plus PB is also greater than its ideal form. When it comes to the negative deviation, it means it is deviated below the ideal line, that is known as negative deviation from Raoult's law. You can observe here the vapor pressure of PA, that is less than XA into P naught of A, P naught A, and here also PB is less than XB, mole fraction into P naught of B. So what happens, this sum of PA plus PB, this is also less than its ideal behavior, that's why it shows negative deviation. Let us see few examples which show such type of behavior. For ideal solutions, this is for ideal solutions. Ideal solutions, mixture of benzene plus toluene and a mixture of hexane plus heptane and mixture of ethyl bromide plus ethyl iodide and chlorobenzene plus bromobenzene, CCl4 plus SiCl4, and all dilute solutions, they shows ideal behavior. It means they follows Raoult's law. And which shows positive deviation for non-ideal solutions, which shows positive deviation. These are the examples: mixture of acetone and carbon disulfide, acetone and benzene, carbon tetrachloride and chloroform or toluene, methyl alcohol plus water, acetone plus C2H5OH, ethanol. So these shows positive deviation, and these also non-ideal solutions which shows negative deviation. Mixture of chloroform and ethyl benzene, chloroform and benzene or with diethyl ether. Next, acetone plus aniline. Next, nitric acid plus water. Next, acetic acid plus pyridine. These shows negative deviation. Next, let us see what is azeotropic mixture. So what is azeotropic mixture? It is a mixture of liquids having same boiling point. So remember this azeotropic mixtures. These are the mixtures, they are having same boiling point. Because of the same boiling point, these two liquids cannot be separated by simple distillation. These cannot be separated because they have same boiling point by simple distillation. We cannot separate these two types of mixtures at different distillation. It means heating at a few particular temperatures. We cannot separate these two types of mixtures because they have same boiling point. Such type of mixtures are known as azeotropic mixtures, and these are mainly formed by non-ideal solutions. Azeotropic mixtures are mainly formed by non-ideal solutions, and one of the most important concept of these solutions are colligative properties. Let us see what are colligative properties. So why these colligative properties are important for a solution? The properties of solution which depend only on the number of particles like molecules or ions of the solute in definite amount of the solvent but not on the nature of the solute. These are given by colligative properties. Understand? What are colligative properties? The properties in which only the number of particles of the solute in a definite amount, you can see, which depend on the number of particles like molecules or ions in a solute in a definite amount of the solvent. So which mainly focuses on the number of particles of the solute which are dissolved in the solvent. That is, those properties are given by these colligative properties. There are 4 types of colligative properties. First is relative lowering of vapor pressure. We have seen in Raoult's law also what is relative lowering of vapor pressure. And next, osmotic pressure, elevation in boiling point, depression in freezing point. So these are the colligative properties which depends on the number of particles of the solute that are dissolved in the solvent. Here vapor pressure, boiling point, freezing point, melting point and osmosis, these are not colligative properties. The change observed after adding the solute, that shows the colligative properties. These are not the colligative properties. These are the properties of dilute solutions in which non-volatile solute without any dissociation or association is happened. See, these are the simple properties of a solution. When there we can observe a change, that gives the colligative properties. Let us see each and every colligative property. Relative lowering of vapor pressure. See, what is relative lowering of vapor pressure? This is applied for a non-volatile solute. When a non-volatile solute is mixed with a volatile solvent, it is mixed with a volatile solvent, the vapor pressure of the solution becomes less than the vapor pressure of the pure solvent. See, the vapor pressure of the solution, it means a mixture of non-volatile solute and a volatile solvent. That vapor pressure becomes less than the vapor pressure of the pure solvent. After adding the solute, the vapor pressure of the solvent gets decreased in its pure form. So it is due to increase in the density which decreases the rate of evaporation. Since we are adding a non-volatile solute to that volatile solvent, its density is getting increased. What happens if density increases? The rate of evaporation gets decreased. That is shown here. The pressure which is inversely proportional to the square root of this density. Here this P0 is vapor pressure of pure solvent. Here P is the vapor pressure of the solvent in the solution. The lowering of vapor pressure, the change in the pressure developed, that is given by the difference between P0 minus P. You can observe here, this is lowering of vapor pressure. We need to relate it. So if we relate it, what happens? It becomes relative lowering of vapor pressure. We are relating it to the vapor pressure of the pure solvent. That is, we are giving ratio to P0. That is P0 minus P by P0. We are relating it to the vapor pressure of pure solvent. That shows relative lowering, how much of pressure, vapor pressure is decreased. That is given by relative lowering of vapor pressure. This is the formula which we get in relative lowering of vapor pressure. This is one of the important colligative property. And next is osmotic pressure. Here osmotic pressure is the colligative property. How we define osmotic pressure? Based on osmosis, right? So let us see what is osmosis. So what is osmosis? Osmosis is a net flow of solvent molecule from a less concentrated solution to a more concentrated solution. Understand this? How a solvent molecule flows from less concentrated solution to more concentrated solution, or from the solvent to the solution, either from the solvent to the solution with the help of a semi-permeable membrane. In osmosis, the main term is this semi-permeable membrane, which is having a porous membrane, helps for the flow of this solvent into the solution. So this flow is known as osmosis. See how a solvent molecule flows into a less concentrated or more concentrated solution through a semi-permeable membrane, that is known as osmosis. Here this is a formula of the semi-permeable membrane, Ce2FeCN6 or Ca3PO4 taken twice. These are the used as semi-permeable membranes. Now from this osmosis we will define osmotic pressure. So what is osmotic pressure? When the column is formed as a result of osmosis, then the equilibrium hydrostatic pressure is known as osmotic pressure. See, when the column is formed as a result of osmosis, while osmosis process is occurring, you can see the flow of the solvent molecules into the solution. It means one column consists of solvent and one column consists of solution. That flow is because of this equilibrium hydrostatic pressure. equilibrium hydrostatic pressure which balances both the solutions, both the solvent and the solution. This pressure is known as here osmotic pressure. The pressure developed at that stage is known as osmotic pressure. So this osmotic pressure is given by Van 't Hoff's equation. So what is Van 't Hoff's equation? Pi is equal to C into S into T, where here pi is known as osmotic pressure, S or R, that is known as solution constant. C is equal to concentration of the solution and T is known as the absolute temperature. Here pi is directly proportional to concentration. You can see here this is the Van 't Hoff's equation where this pi, the pressure applied, is directly proportional to the concentration. Concentration, how we can define concentration? Number of moles by volume, that is the concentration. If we substitute this in this Van 't Hoff's equation, what we get? Pi of V is equal to N of S of T, where N is number of moles of the solute and V is the volume of the solution. So here if we further apply number of moles is equal to weight by gram molecular weight, in that way we can define this Van 't Hoff's equation for osmotic pressure as pi into V is equal to W by M into RT. So this is the Van 't Hoff's equation for osmotic pressure. This is also important equation, remember it. And next one more colligative property, that is elevation in boiling point. How we can see elevation in boiling point? Suppose if in a solution we observe boiling point is the temperature of a liquid at which vapor pressure becomes equal to the atmospheric pressure, equal to the atmospheric pressure. At that point what happens? A liquid will be boiled when the vapor pressure is equal to the atmospheric pressure. What happens here? You can see the graph here. There is a graph between vapor pressure and temperature. You have two boiling points. One of the boiling point, one of the line is for solvent and one is for solution. What happens here? After adding the solute, here we are adding solute. What happens if we add solute? The boiling point of the solution will be increased. It means it is elevated. That elevation in the boiling point is the colligative property. You can see here the elevation in the boiling point is given as this delta TB is known as the elevation in the boiling point, that is directly proportional to the molarity of the solution. A molality. See here m is small m is molality, that is directly proportional to the molality. Here delta TB is equal to, this is the constant. This constant is known as molar elevation constant or ebullioscopic constant. This Kb, delta TB is equal to Kb into m. Here delta TB is equal to Kb into W by m into 1000 by W. So this is the formula to calculate elevation in boiling point. And next, so remember this formula to calculate the elevation in the boiling point. Here W is known as weight of solvent, capital W is known as weight of solvent, this is also m, and small w is weight of the solute. Kb is known as molar elevation constant. And next, depression in freezing point. So what is meant by freezing point? Freezing point is a measure of temperature for a substance having same solid or liquid forms in equilibrium and also have same vapor pressure. At that point at which solution forms, at which there is a lower in temperature because of the lower in vapor pressure of the solution. A solid form of a solution that separates out at lower temperature because of lower vapor pressure of the solution. That point is known as a freezing point. You can see clearly a graph here, a graph between vapor pressure and temperature. See, this is the actual freezing point. This is the actual freezing point of the solvent. What happens if we add a solute here? Its freezing points gets decreased. See here, this is the solution freezing point. This solution freezing point will be decreased. That is given by this colligative property, depression in freezing point. That depression in freezing point is denoted by delta TF. You can see this is also directly proportional to its molality. Here this is equated by the constant Kf. This Kf is known as molar depression constant. This Kf is known as molar depression constant. In elevation in boiling point, that Kb is known as molar elevation constant. Here Kf is known as molar depression constant. Similar formula is applied here. This delta Tf is equal to Kf into W by M into 1000 by W, since it is depending on molality. So this is the formula for depression in freezing point. You can see here how vapor pressure, freezing point and boiling point will be affected. Here in this picture you can see this vapor pressure. If we add solution and solvent mixture, because of the vapor pressure, relative lowering of vapor pressure, this type of solution will be formed here. When solution is added to the solvent, what happens? Vapor pressure is the pressure of the vapor over a liquid at equilibrium. This is the definition of vapor pressure. If a non-volatile solute is added, this will lower the vapor pressure of the solvent. That is the relative lowering of vapor pressure. Next, freezing point. If the freezing point is of one solution is at 0 degrees centigrade, if we add solute, it will be reduced to -5 degrees centigrade. That is depression in the freezing point. For boiling point, there will be elevation in the boiling point. If this is the boiling point of the solvent, if we add solute to it, its boiling point will be increased. There will be elevation in the boiling point. See, for solvent it is 100 degrees centigrade. If we add solute, it becomes 105 degrees centigrade. It means the temperature is increased. That is the elevation in its boiling point. So these are few colligative properties, important colligative properties of this solution. And we have one more important term, that is Van 't Hoff factor. These colligative properties are directly proportional to the number of moles of solute, dissociation or association. Right, as we have seen the colligative properties definition, it is mainly depending on the number of moles of solute. What about this Van 't Hoff factor? This Van 't Hoff factor is a factor that takes into account of this abnormal behavior. The abnormal increases or changes in this colligative properties, thus that is taken by this Van 't Hoff factor. So let us see what is this Van 't Hoff factor. That is denoted by I. Here I is equal to observed magnitude of any colligative property divided by normal magnitude of the same colligative properties. Is the ratio of the observed value to the actual value. When it is compared with the molar mass, this I is equal to molar mass by observed molar mass. So this is the definition of this Van 't Hoff's factor, and thus you can observe here, when this value of this Van 't Hoff's factor I is equal to 1, then the solute remains unaffected in the solution. The solute remains unaffected in the solution. When this Van 't Hoff's factor value is greater than 1, then the solution undergoes dissociation. If I is less than 1, then the solution undergoes association. So this is the value, the main concept of this Van 't Hoff's factor. If the values of I is equal to 1, the solute remains unaffected. It remains normal. How we are added, it remains in that way in the solution. If it is greater than 1, it undergoes dissociation. The breaking of bonds may be formed. If I is less than 1, it undergoes association. New bonds will be formed. In that way, this Van 't Hoff factor can be determined. You can also determine here degree of dissociation alpha with this Van 't Hoff's factor. This degree of dissociation is denoted by alpha, that is equal to the value of this Van 't Hoff factor I minus 1 by n minus 1, where n is number of species formed after dissociation. This is degree of dissociation, and we have degree of association alpha, that is equal to n of 1 minus I by n minus 1. So this is the formula for degree of dissociation. Here I is the Van 't Hoff's factor and n is the number of species formed after dissociation. So these are the few concepts of this solution. I hope you revise all these concepts and remember the formulas, so you can easily answer the questions in your exams. Thank you for listening.